Hello everyone, welcome back. Today we are continuing exploring closed-loop optimization. In particularly, we're going to go through a few examples on Bayesian optimizations in real-world research and development projects. We're going to discuss how Bayesian optimization can be used in material discovery, process optimization, as well as at a larger scale for battery fast charging. Let's dive in. So we've been discussing about Bayesian optimization. In a way, it's very powerful. It helps us to link the input x and our observables or our target y, which can be noisy, and maybe we have a small data set. We have a black box function, and we can iteratively learn from our previous data collected and trying to optimize towards our target, our objective function. So often we'll go through a series of steps to conduct a Bayesian optimization process. We'll start with formulating our challenge into the goal for our optimization algorithm to try to reach. We'll start taking some initial data set to build a surrogate model, which is an approximation of the true function. We don't know. Because the true function at this stage is a black box function, we are trying to fit and trying to understand what is the input and output relationship. And that will be followed by choosing acquisition function. In a way, acquisition function is a rule to help us to select the next round experiment based on our surrogate model. From here, we can select our next round experiment. We update our surrogate model with the new data collected until we reach our stopping criteria, where we say, hey, we already achieved the optimized property of interest, or we say we are running out of our experimental budget, so let's stop there. So that's our stopping criteria, but by then we will completed our closed-loop optimization steps. So with this in mind, so how do we start? In real world, now we have engineering challenges. So often we'll start with our problem formulation. We'll start with answering the questions of what's our objectives, right? What we are trying to achieve. What's the input parameters we are tuning to achieve our goals? And what is the search space? In other words, what's the boundaries within which we are trying to find our optimal solutions? With that in mind, so the first case study is that we can use Bayesian optimization in material discovery. So in this specific case, we are navigating a large compositional space. So here, the example shown on the screen is a multi-carton perovskite semiconductor. It contains cesium, methylammonium, and formaldinium in its chemical formula, but the ratio between the cesium, the formaldinium, and the methylammonium is not fixed. So in other words, we are trying to tune the composition of this material with the hope that we can optimize for the environmental stability of this perovskite semiconductor. So in other words, the input in this case are the compositions. So there are 3 different compositions, but in fact, 2 of them are independent. The third one is 1 minus the composition of the previous 2. And our output, what we are trying to predict and trying to optimize, is this a metric called instability index. In other words, we experimentally measure when our perovskite semiconductors degrade, and that gives us a metric of how unstable they are under a hot climate and also humid climate. So this is our optimization challenge, which is to find the optimal composition that leads to the most stable perovskite semiconductors. So this is an example taken from one of my early research, which is really about to build a Bayesian optimization framework. So we make some samples. In this case, you can see a start in this triangle shows the compositional space. We collect equally spacing compositions. the first round, we collect our initial data, and then we make measurements. In this case, it is the stability of the process semiconductors. And with these measurements, we build a Gaussian process regression model. That's our circuit model. And with the model, not only we know what is the posterior mean, which is the predicted value of our stability based on each composition of interest, we also know the uncertainty, which is shown at the corner diagram. So you see, after the initial sampling round, we can see the compositions we measured have a very low uncertainty, and the compositions we didn't measure have a high uncertainty. From there, of course, we move to the decision-making stage, and in this case, we use acquisition function. A popular acquisition function is expected improvement, which balances the exploration and exploitation. And we take the suggestions from our acquisition function, and then we make the measurement again. So you can see this can be an iterative process until we converge towards the most stable compositions of interests. But what's interesting about this case study is that not only we just did the steps which we just explained, the conventional Bayesian optimization, we have to bring another information source. So here on the screen, you see DFT modeled phase stability. So DFT, this is the density function theory. So this is a first principles calculation of how stable the process semiconductors are. But in short, so what we did is we take this additional information from the first principles calculations, and then we use it as a probabilistic constraint to the acquisition functions we got from the experimental data collection. And that leads to a new acquisition function, which obtained from two different data sources, the calculations and the experiment. And then we use this combined acquisition function, which and then to optimize from there. You can see the first round, second round, the third round, and we land this optimal compositional region. So in this case study, what it shows is that in real-life Bayesian optimization scenarios, we are building this closed-loop optimization, make sample, measure it, which gives us the input and output, and make a prediction using a circuit model. Then we decide the next round experiment through the choice of acquisition functions, ranking the potential experiments, and trying to guide us to make the next sample. In addition to that, we also have our first principles calculation, so which is additional data source, and we use it as a constraint to help making the decisions to decide which experiment to do next. So in this example, with additional data source, it accelerates the optimization process, so it makes the convergence faster. So you can see this is we start to build on the conventional Bayesian optimization with additional elements to make it more practical and more effective. The second case study I'm introducing is in the process optimization space. So in this case study, our input is a series of processing windows. In this case, we are again trying to make a process semiconductor film, but instead of changing the chemistry, we are changing how these films are made. We are interested in tuning its annealing temperature, annealing duration, the anti-solvent drop time, the relative humidity, and all of these processing parameters would affect the quality score of how well the final films are. So this is kind of a common example in engineering practice where we have a series of processing parameters, and we are interested in optimizing within this multi-dimensional space. So this case study is drawn from a recent research paper from our own group in collaboration with researchers from the Lawrence Berkeley National Laboratory. So in this study, the researchers tried to experimentally sample in this 4-dimensional space and then experimentally measure the quality of the resultant thin films. What is interesting is that in this study, our stopping criteria is not when we find our global minimum or global maximum within this parameter space. Instead, we use the KL divergence, which is a measure of how much our Gaussian process regression model is changing after each batch of new experiments. So the idea of this study is trying to learn the process parameter and the film quality relationship. And in this case, the use of Bayesian optimization allows us to sample less than 1% of the possible conditions in this 4-dimensional space. And then we realize, after this less than 1% of sampling, and the learning rate, in other words, the total information gained, is gradually converging. So in other words, the learning rate dropped after you see here after 5, 6 iterations, we are already reaching our diminishing returns in terms of how much more information we are gaining. So at that point, we are confident, we have a good understanding of the overall processing parameter to our film quality relationships. So in this case study, you can see there are two things which is interesting in terms of designing the Bayesian optimization framework in real life R&D projects. First, is that we are, instead of doing Bayesian optimization by sampling one more experiment each time, we're using batch Bayesian optimization. In fact, the experiment was conducted by a thin film deposition robot. And the paper presented here is published in the reference below if you want to check it out. So here, instead of make and measure, we have an automated experimentation platform which will combine the making and the measuring process through this thin film deposition robot. And with that in mind, so we can have each round of Bayesian optimization, our algorithm model is updated from a batch of the sampling. So in this case, we can do multiple automated experiments and then have it input into our algorithm model and then to decide the next round of experiment. Second thing which is interesting about this design is when do we stop our experiment? There are different stopping criteria depending on the real problem, real challenge in the practice you are interested in. You can set customized stopping criteria which would allow you to say at this point, let's stop our closed loop optimization and we exit the loop where we say we already achieved our goal of the experiment. Let's move on. The third case study I want to share with everyone is that beyond the materials and the kind of process optimization of making thin films, here is another example which allows us to use Bayesian optimization. In this case, it is to optimize the battery charging protocols. So in this case, again, we have our input and output. The input in this case is how do we charge a battery. So we have CC1, 2, 3. These are individual constant current steps. So when we charge our battery, as the battery gets charges, we divide this charging process into the initial constant current step and followed by several sequential steps. And each of these parameters can be tuned. So you may be familiar with the idea if you charge your batteries too fast over a long run, like it would potentially damage the battery lifetime. And this is definitely one of the studies to allow us to tune how quickly we are charging our batteries, and then to see how it impacts our battery cycle life. So in this case study, we are trying to maximize the battery cycle life. In other words, we are trying to have our batteries to last as long as possible by tuning how we charge our batteries. How does it work? So this is a study from a publication with the reference shown at the bottom of the slides. It's a study from Stanford, MIT, and Toyota Research Institute. And what the researchers did was that they first have batteries cycled over years, and then instead of having the battery to have already degraded at the end of its lifetime, they built an early predictor. So in other words, they have this early prediction model which shows the expected battery cycle life as our Y, our output. And then we have the Bayesian optimization, optimize the 3 parameters, CC1, CC2, and CC3, which are the charging steps being used as the input. So in this study, you can see a key challenge of optimizing battery charging for battery lifetime is that batteries can take years to reach the end of lifetime. So if we just wait until all the batteries reach the end of life, it's a long time. So when we consider to optimize the battery charging using Bayesian optimization, so we have the make, these are the battery samples, the measure, which is supposed to be how long the battery lasts over years. So instead of the actual measure, the researchers have an early prediction model. And then we use the predicted battery lifetime as the output of our Socrates model. And then we have the decision of how do we optimize battery charging from there. So this is kind of an example where again, we start to build extra components around our closed loop optimization strategies for it to account for the real life constraints and real life scenarios. So with these case studies, so I want to kind of bring everyone's attention to a broader context when it comes to real world optimization. So real world optimization tasks can be complex. So in this lecture, we discuss about the use of Bayesian optimization to have the iterative learning, to have the optimization with the idea for it to be data and cost efficient. So in real life, there are a lot of the nuances we need to consider when we are building our closed optimization strategies. So we need to consider the throughput of our hardware. Often that can lead to variable batch sizes. Also, our measurement can be multi-fidelity. So in the way they can be multi-modal and they have different level of fidelities. Our goals of the optimization may be multi-objective. So we will be trying to optimize different materials properties at the same time. And Bayesian optimization definitely allow us to account for that. We may have our input to be mixed, continuous, and categorical input. So we need to consider what is the scale and also the type of the input parameters. Often there are constraints either from the physical hardware or from physics. And that also leads to another aspect is that physics-informed machine learning has become more and more popular among engineers trying to apply machine learning in real world problems. So we can think about how do we incorporate our prior knowledge about our physical systems when we design our optimization strategy. Of course, the interface of hardware is another like a very interesting topic because like we can implement our closed loop optimization strategies on our robotic systems, and in this way, we start to form this like robotics for execution, and then AI and machine learning for planning, and the whole closed loop optimization cycle becomes an autonomous system which further advance our idea of automating our like experimentation to help us to achieve our optimization goals in real life engineering practice. With that, thank you very much for listening, and see you next time.